in working on a PhD in civil engineering with a focus on transportation engineering. And today I will be presenting some work we've been doing with the Virginia Department of Transportation on the use of immersive virtual technologies for public engagement and a state of practice review of U.S. state departments of transportation. All right. So I'll start with a little background and then talk about the application that we've been doing in Virginia, and then get into the methodology and results of the state of practice survey and kind of where that's headed. So this is a research team that's been working on this. It's made up of UVA faculty, VDOT staff, and then student researchers, including myself. So probably anyone who's worked on transportation knows public involvement is essential for transportation planning to incorporate community perspectives into project decisions. That said, a lot of traditional 2D plans and maps often fail to clearly communicate complex technical information to the public. And so a lot of agencies are starting to look at these more immersive virtual technologies, including VR and AR mainly, that offer an enhanced way to visualize design alternatives and simulate future transportation environments before they are developed. Um, and some previous research has shown higher public engagement and improved comprehension when 3D and VR visualizations are used, although research is limited and still being developed for the transportation application specifically. So this kind of started because in our lab group, we've done work with VR for other transportation applications in Water Street, and being able to recreate what different scenarios in a virtual reality and see how people engage and interact and use spaces. So this is an example from Charlottesville, Virginia, where UVA is located. Um, and creates a kind of a easy way to see how design changes. So this is an example of you can once it's developed, you can just click the button and see how people use the bike lane versus not the bike lane when
Carreen,
there's no bike.
your screen isn't sharing.
Oh, okay, that's good to know. Thank you. I don't know why that is. Let's see. It says it is sharing to me. Let me stop and do it again.
Oh, never mind. Sorry, there were multiple tabs, multiple screens sharing.
Okay, okay, one second. Let
Thanks.
me get it back up. Um,
Hi, Carreen. The presentation was going quite well.
okay, okay, cool. I think let me just get it back up then, and we will get back.
We were able to hear you and listen and see your slides very well.
Okay, great. Let me get back to that side then. All right, so this is the example of the work we've done, and so VDOT was interested in seeing if this work could be beneficial for the public engagement and applying it to a real project. So, just as an example, kind of what the kind of work we were these we're talking about when we do the survey. This is the project in Bristol, Virginia, and they were interested in applying um, the technology to this proposed roundabout project. And it is the first roundabout project in Bristol, and it kind of had this high profile project and need for explaining the design to the public to really help them understand what was happening since it's kind of a new infrastructure type that a lot of the residents might not have been exposed to. And so this is, that traditional 2D plan that you see, and with an engineering background, you can kind of tell mainly what's going on. But for a lot of people with an untrained eye, it can be difficult to really understand what's happening and cause confusion. And so this is just some examples of our VR environment, and participants were able to go in and experience the world and the infrastructure changes before anything happened. So that's just a little example. I'm going to see if I can get this to play the actual, there you go. So we have a bike simulator, a pedestrian simulator, and a driving simulator. And users are able to experience the environment virtually. So I'll just play a couple seconds of this to give you guys an idea. So we're able to put in all the different infrastructure elements and really translate it into this 3D space. All right, pause that. And so that was before we did this project, we wanted to start off with just understanding what the current practice was. What are other DOTs doing? What is the status of it and lessons learned? And so really the goals were to assess the current practices of these immersive virtual technologies for public engagement in transportation projects specifically, and identify the institutional, technical, and practical barriers to implementation across state DOTs. And then document those benefits, limitations, and lessons learned from practitioners with direct experience using these tools, and ultimately be able to provide recommendations to support more effective, widespread use of immersive technologies in transportation planning and public involvement. So we started with sending out a survey to as many DOTs as we could get a hold of, and we've had a few additions since the completion of everything, but so we were mainly focusing on places who had some kind of work, some sort of project that they'd done. And so we ultimately had 33 responses, 14 DOTs. Some of the DOTs had worked with other universities and consulting firms to do this work. So we also had a handful of interview responses from those groups. A majority, as you might expect, started using the technology fairly recently. Washington State DOT and then the University of Alabama had been using the technology the longest, but for the most part, people were really starting to adopt this in the last 10 or fewer years. One of the agency capacity was one of the big barriers that a lot of DOTs listed. And just having limited capacity for using this new technology. But if you had internal teams that had been really dedicated to this kind of work, so Washington State, Caltrans, and North Carolina DOT all had teams dedicated to this, and then some of the consulting firms as well had example like digital experience teams. But typically, we had most respondents listed that less than 5 employees that really had knowledge of this topic. There's still a wide range of software used. So there's the headsets part of it for VR, and that had a little bit more of a common theme with the Oculus and HTC Vive Pro and the Meta Quest having the most usage. And then some also preferred tablets for larger public meetings because it's a faster handoff. And then there were some just hygiene concerns with having a ton of users. And then the visualization, realism, and detail determined by the setting of the projects was another consideration that was really taken into account with sometimes with more detailed renderings of urban context versus rural areas with less elements that need focus. So that could also influence the software used. And at this point, with it being such a new technology, a lot of people are kind of using different things. But Unreal and Unity and SketchUp are kind of the more common ones, though it was pretty widespread. At this point, most places said minority of projects or no projects at all for which projects are being used with VR. And then there's a little bit more common usage of 3D visualizations for a majority of their projects. And North Carolina DOT and Iowa DOT indicated that they were, after a few projects of having a lot of success, they started using them for all their projects. So some of the common factors that we saw from the responses was these key factors of VR and 3D visualization use are the size and complexity of projects. So the larger, more complex projects really motivated the VR use. Social and environmental impact, when there was a greater impact, that also motivated the VR use to address those concerns and help understanding. If there's the need to really get public understanding and engagement, with the public VR was helpful to really alleviate opposition. Budgeting was something that was could limit the VR use, especially for smaller projects. It just wasn't worth um, the time and effort. But so typically we saw the projects using this technology were those larger high impact ones. And then project phase was another thing that came up a lot of that if there is an earlier um, simpler visualizations were sometimes used earlier in phases, and then that getting that more detailed visualizations could benefit projects in the later phases, um, and more likely to have VR or 3D visualization if the modeling was done during the engineering process because you already had you already put that time into that. For funding, DOTs mainly use VR. For the higher projects, the cost of developing visualizations is relatively low once you have the staff knowledge, is what a lot of respondents discussed, and pays off by avoiding the costly delays, confusion, and other public opposition. Internal teams were the most cost effective. There are a few DOTs that had started implementing that. And they recommended this hybrid approach during the early adoption because it can be hard to get off the ground. So some examples of significant public engagement projects. So there's a wide variety of immersion and interaction, but some of the more interactive and fully immersive ones they were used for this I-75 Mississippi River Bridge, the I-69 Ohio River Crossing, and Project Neon. And then the I-440 Interchange Project. Um, and then it's also possible to have kind of that interactive simulation, which Caltrans had a few examples of, and having the 3D rendering that people can explore the new project without being fully immersed. So we also asked the practitioners about the future of immersive virtual technology, and there was a clear recognition of the benefits and potential of using immersive virtual technology. Nevada DOT and North Carolina DOT now incorporate the virtual immersive technology to some extent in all projects following their successful use. And a lot of people that we discuss that it's really transforming public engagement and that technology is evolving rapidly and will make it more welcoming as it continues to develop, that it's particularly helpful for unfamiliar infrastructure like DDIs or roundabouts. And one JMT employee believed it was as ubiquitous as that it will be as ubiquitous as people starting to use smartphones. So it's really starting to grow in popularity. Augmented reality has limited existing use, but was commonly mentioned for its potential, and having digital overlays that proposed project sites could make benefit stakeholder support. And another one that kind of surprised me was the potential use of environmental permitting at early stages of projects. Um, and a lot of the projects kind of stemmed from that environmental side to begin with, and construction inspection in later stages of the project. Um, so finally, adoption of NVR and AR is still relatively early stages for many organizations, but an overwhelming majority of VR applications was for public engagement. Um, Design review was something that we also asked about and was a little bit more limited. Um, there's still limiting little consistency in the software and hardware used. And largely we found that there was this lack of metrics to measure um, efficacy and value of technology use. And most people had really positive things to say about it, but that there was really limited studies on um, more quantitative metrics of its success. So there's a strong potential for immersive virtual technology to really transform public engagement in transportation. It can enhance the understanding of complex projects and reduce opposition. It's effective communication and transparency with community, and efficiency of project management, especially with the early adoption. That said, the barriers, like I discussed, was the cost and resource limitation is really one that came up a lot, and but people mentioned that it can be mitigated by bringing visualization to earlier project phases. So that is something we are now working on. The project that I talked about at the beginning, we took to a public engagement meeting for this Bristol roundabout project, and we collected responses and took collected eye tracking data on their experience in the simulators. And so that has been people found it really helpful in giving them a sense of how the future corridor would look. And people commented on the visualizing the proposed changes that it was really helped them understand how roundabouts function and understanding how to interact with vehicles in the crosswalk, and seeing the safety of the splitter island. And yeah, it was helpful to look around and not be limited to one fixed perspective. So that's a project we're currently working on. I'm currently doing the data analysis for, so that is the next paper. But that's kind of the direction this is going, and starting to get more quantitative metrics on the success of and benefits of using this technology. If anyone's interested in this work more, there is a newly a new working group called the National Transportation Visualization Working Group um, that we have started working with. There's a few folks out west that are really leading this, but if people are interested in joining any of those meetings, I would recommend it. And if you have any questions about the lab that we have at UVA, that's our website and my email address. And I'll stop there and open it up to questions if we have time. I don't know how we are doing on time with this slow start.
Thank you very much, Carreen. Was a great talk, and I wonder if there's questions from anybody in the audience today. As Lika was saying, you can also put your questions in the chat, so it could be a more maybe more effective way of using the time we will have. Since we're a little bit behind the schedule, I would like to ask for questions for Carreen through the chat, unless I see any request, and then move to the second talk, where I understand that we have Yu Wang. Is Yu Wang here? I see him or him. So Yu Wang is the leading author of a group of 5 researchers from the University of Leeds. And the talk, you please, if you could share your screen, that would be great. The title of the presentation is related to the one we have just heard, is Connecting Visual Attention to Choice, uncovering why interventions work or don't through eye tracking in virtual reality. So you, please.
Thank you, Chair. Can everybody see my screen?
Yes.
Okay. Okay, thank you. And thanks, Chair. Thanks, Carreen, for introducing the virtual reality scene and the eye tracking scene. And it's good for me to save some time introducing this. And today I'm going to present our work with Dr. Thomas, Albert, George, and Professor Christopher Choudhury. The work on connecting visual attention to travel choices. In particular, we use eye tracking data to better understand why behavioral interventions work or sometimes don't work, and explore how this information can be incorporated into behavior models. Let's start with a simple question. Why does an intervention work or not work? Normally, we observe the interventions, attributes of the alternatives, and the final choice. But the actual decision-making process in between is largely unknown, and we traditionally will use some econometric behavior models such as the random utility maximization models to model the choice probability. In particular, when we talk about interventions, we want to know, did people pay attention to the intervention? Did it matter to them? And was the effect strong enough to change their choice? So this leads to two main methodological questions. First, how can we capture attention and perception of the interventions during the decision process? And second, how can we incorporate this information into a model of deliberations? There are a lot of potential ways to answer these two questions, and today I will give a case study here. For the first question, we use eye tracking data. Eye tracking allows us to identify what people look at, how their attention is allocated, and roughly how much visual information they receive. So it gave us a way to move beyond simply knowing whether an intervention was presented towards understanding whether it was actually attended to. For the second question, we use decision field theory. It's a mathematic psychology method. Unlike a standard static choice model, DFT represents choice as a dynamic preference accumulation process, and preferences are rapidly updated as people consider different attributes until the decision process ends. Importantly for our study, DFT includes parameters related to attribute attention, attribute importance, and process noise. This gives us a natural way to connect eye tracking data with the decision-making process. This brings the two parts together. Rather than treating the eye tracking data simply as another explanatory variable, we use it as a proxy for the underlying decision process. Specifically, we explore whether visual attention can inform the process parameters in DFT, helping us understanding not only whether an intervention changed the choice, but how it changed the decision process. Now I will introduce our data and the experiment. In the experiment, we ask a participant to make choice between a high carbon emission travel mode taxi and a greener travel mode bus. In each task, participants first choose between the taxi and bus based on time, cost, and carbon emission in SP choice showing in the virtual reality hide site on the screen here. And the red part shows the main elements we collect the eye tracking data. We record the attention duration they paid attention to these different areas. And then after they make the choice, they then experienced their chosen mode in the virtual reality, and afterwards made the same choice again for a return trip. And this time, we gave them an opportunity to revise their choice. And if they chose the taxi, there may be some nudge interventions during the virtual reality experience part. And I will introduce the interventions shortly later. For each participant, there are 6 choice tasks, and in each task, there is an initial choice and a reversed choice. So for each participant, we have in total 12 choice observations. And the first intervention we used is a pre-trip carbon tax nudge. In the control conditions, the taxi cost is simply shown as a fare, and in the treatment conditions, the total cost stays exactly the same, but it is split into the fare and a separate carbon tax. So the intervention changes the salience of the environmental cost rather than the actual price. The second intervention occurs during the virtual reality journeys and contains 2 elements. The first element is a static poster shown to the participant while the participants are waiting for the taxi to come to pick them up. And in the treatment condition, the poster provides an environmental message encouraging lower carbon travel, reduce carbon emissions, save our children's future. And in the control conditions, there is only an irrelevant poster. The second enrolled notch element is a dynamic carbon meter inside the taxi. Instead of a one-off message, this provides a continuous feedback on accumulated carbon emission during the journey. And there is also a leaf change the color when the carbon emission accumulated reach different threshold. And in the control condition, there is only an irrelevant label here. And the final intervention appears after the taxi trip in the form of a receipt. In addition to the Euro travel time and fare, which is the control condition, the treatment condition provides carbon emission feedback and a social norm message. The number of people using public transport is 5 times that of taxi. We had in total 105 participants, and for each participant have 12 choice observations. And we have in total 4 groups received different combinations of these 3 nudges. And the first 2 of the task always contained no intervention as control conditions. And the amount of intervention then increased across later tasks. This gave us variations both across participants and across repeated choices. Before modeling, let's first look at the descriptive patterns. This figure shows the proportion of participants who initially choose taxi, but then switched to bus in the reversed choice. The shift rate tends to become higher when interventions are introduced, particularly in the later tasks when in-route and post-trip interventions are combined. We can see this part is much greener than the observations without the nudge. We then look at where participants actually paid attention. Overall, the time and cost, these 2 attributes receive more visual attention than the carbon emissions. And we also see that much more attention in the initial choice than in the reversed choice. And attention generally decreased across tasks, suggesting that participants become more familiar with the choice situation over time. And looking specifically at the pre-trip nudge, the carbon tax presentation clearly attracts additional attention. The x-axis is the different task, the y-axis is the duration in seconds, and the blue bar is no intervention conditions, and orange is the with intervention conditions. And for the in-route intervention, the 2 elements shows different attention patterns. For the poster, attention is very similar with and without the information. But for the carbon meter, participants spend more time looking at it and when carbon feedback is provided. Finally, for the post-trip intervention, it seems that it redistributes the attention across the receipt. Without the intervention, participants focus mainly on the standard travel information. But with the intervention, the attention shifts towards to the carbon labels here and the social norm message. So these descriptive results show how difference in visual attention. The next question is whether we can use this information directly in the choice model. We construct 2 types of eye tracking variables. First, for each nudge, we measure the proportion of attention allocated to its specific elements. Second, for the SP task attributes, we measure the attention allocated to time, cost, and carbon separately for the initial and revised choice. And for the model, we construct a hybrid DFT model considering the initial choice and the revised choice together. and use a stickiness parameter delta to combine these two structures to see whether the choice in the initial choice will have insistence effect on the revised choice. And here we incorporate the eye tracking data in 3 places. First, the attention to the pre-trip nudge is linked to the cost effect. Here, the blue part. Where attention to the in-road and post-trip nudge affects the starting preference for the revised choice. In the see the orange part. Finally, attention to the SP attributes is used to inform the DFT attention weights. It captures how much attention the participant allocate to each attribute. And this figure shows the this part. This figure shows the preference updating process in DFT. We start from an initial preference. At each step, this is updated through a preference feedback and a new valence parameter here, depending on the attribute being considered. And this continues one step by step until the final preference is obtained and the choice is made. For more detailed methodological details, please refer the paper by Thomas. Now let's move into the results. First, higher cost and longer travel time significantly reduce the preference. And the carbon emissions, however, don't have a significant effect on choice. The positive shift parameter here, we use the basic parameter, add a shift parameter to see whether this preference change at the reversed choice compared with the initial choice. The shift parameter suggests that the negative effects of cost and time become weaker in the reversed choice, maybe because the people are more familiar with the choice decision process. And for the pre-trip nudge, attention to the carbon time information doesn't significantly affect the taxi preference in the initial choice. However, the negative shift suggests that its effect becomes more negative in the reversed choice, potentially reducing the preference for the taxi after the travel experience. This highlights the importance of using virtual reality to give the participants a more realistic experiment experience. And for the in-road nudge, we see a clear difference between the two elements. The attention to the static posture has no significant effect, while the greater attention to the dynamic carbon meter significantly reduced the preference for the taxi. This therefore lowers the probability of choosing taxi in the revised choice. And we found a similar pattern for the post-trip receipt. Attention to the standard travel information has no clear effect. In contrast, greater attention to the carbon emission information and the social norm message reduce the preference for taxi, with the norm message showing the stronger effect. So eye tracking helps us to identify in which parts of the receipts are actually associated with behavioral or change. And in traditional variable, we can only have one dummy variable for this kind of taxi receipt and can't split out the effect of different elements here. And we then use eye tracking to directly inform the attention weights in DFT. The positive and significant alpha means that the more participants look at an attribute, the greater the probability that this attribute is attended to during the preference updating process. And the shift is not significant, suggesting that the gaze attention relations remains broadly stable between the initial and the reversed choice. Finally, the insistence parameter is positive and highly significant. In other words, if a participant initially chooses a taxi in the initial choice, the participant would like to stick to this choice in the revised one. We did some further tests, for example, extended this static model to a dynamic model, considering all of the choice among the 6 choice tasks one by one, this structure. And we also compared the different model construction structure with basic MNL models. And the findings, limited by the time, I can't show the details here. And the findings shows that eye tracking data help improve the models both for the MNL model and the DFT model. And the DFT model, because of the nature of the parameters to capture the deliberation process, it can slightly better integrating the eye tracking data compared with the MNL model. And the model is clearly improved by incorporating the dynamic nature of the decision-making cross-task compared with the static model structure. And finally, the eye tracking help understand which intervention elements work or don't. Thank you. And we also have some video recordings for these participants, for these experiments from the view of the participants. If you have any interest, please contact me and can have a look of the video here. Thank you very much.
Thank you very much, you. Again, if we have questions for him, I would recommend to go through the chat. I posted some question for Carreen before, so it would be great if we can interact there with some questions for this for the authors. The third talk today comes from MIT, from Jung-Hoon Cho.
Hello.
See here is AGORA. Can deliberation and governance gates absorb participation bias in transit planning? So please, Jung, go ahead with your talk.
All right. Thank you very much. Yeah, good afternoon, everyone. My name is Jung-Hoon, and I work with Cathy at MIT. This talk is about like one very practical question in public engagement process during the transit planning. If the people coming to the public hearing meeting are not very representative to the population, we want to see if like whether better planning process structures still keep the final plan outcome stable and fair. Yeah, so let me start with one local example here in Massachusetts. A few years ago, the MBTA, Massachusetts Bay Transportation Authority, has tried to do the bus network redesign. And as many of you may know, the bus network plan is not just produced by an algorithm. It has to go through a lot of processes like public hearings, community inputs, revisions, and political review before them like being implemented to our cities. So, if the different people show up to those meetings and they often speak for the routes that matters most to them, which makes sense. That is normal. But it means that the meeting may not represent everyone affected by the plan, by this new revised bus network design. So we wanted to see if some structural process in these transit planning can resolve those biases. So yeah, I start with the formal definition of our problem, which is the transit network design problem, or TNDP, where we begin with the transit graph, node and edges, OD demand queue, and the operating constraints, and the decision is the route set and the service frequencies of the bus. And we evaluate a plan using passenger cost and operator cost, and we want to minimize both of them. And the evaluation metrics would be like those costs, service coverage, and the feasibility of the plan. This is, of course, an NP-hard combinatorial optimization problem, but it is also a mature optimization problem with many established methods can solve. But the important point for this talk is that optimization does not make the final decision by itself. Agency has to go through a lot of like public hearing procedures and go through some political review process. And also agencies do this redesign transit network very occasionally, like every like 10 to 20 years. So, who shows up can shape what gets built. Prior works find that the public meeting participation is systematically skewed towards older, higher income, and car-owning residents. In transportation planning, this means the meeting composition is an uncontrolled input to the planning process. So the issue is not that participants are wrong to express their own needs. They can do that. But the issue is that a small self-selected group may overrepresent some of the group and underrepresent the others. Agencies then revise the plan based on those public meetings, comment periods, and the board votes. But usually cannot rerun the same process with the different audience, like with the different meeting groups to measure the sensitivity of like who shows up to the meeting. So like that's where like LLM can replace those process very efficiently. So like even with the same network and same travel demand, we don't know like how much adopted plan depends on who happened to be in the room. So during this talk, I will ask three questions. First, when we systematically change the meeting composition, for instance, the meeting can be held in weekday 1 p.m., weekend 1 p.m., weekday 7 p.m., they could result in different results. So how much do the planning outcomes change depending on these compositions? The second question is, does the deliberation affect the outcomes? Does the composition matter when the participants can critique and revise the plan? So yeah, on the right, we sample a meeting from the population, and then the participants deliberate and react to the initial plan, and agencies will write the revised plan. Okay, and after the plan is revised based on some deliberation process during the meeting, some gates has to be checked. For instance, the consensus of the like during the meeting, or the fairness criteria, or whether it meets the Title VI like analysis to determine whether it can be accepted in the real world. So the third question would be, can those explicit governance gates reduce any remaining cross-profile variations? All right, so yeah, if you look at the top row denoted by parentheses A, status quo, it is close to the current practices. Self-selected attendees come to the meeting, make some comments, and the staff from the agencies or from the DOT summarizes those comments, and then the plan is revised based on the the summarized comments. But in our proposed framework, we make each step very explicit. So we keep the transit problem fixed, and then we vary three things. One is who participates, like who comes to the meeting, who voice up during the meeting. And then two, whether the deliberation is enabled or not. And three, whether the acceptance governance gates are used. So this let us compare the processes under the same technical conditions, like the same problem we are solving. So yeah, let me like go into details on the deliberation loop. So first, a planning agent proposes a route set. And the second, it is evaluated based on some TNDP metrics. For instance, as I mentioned earlier, passenger cost, operator cost, service quality, or fairness. And then the third, LLM-enabled persona agents read those results and write the critics and vote. And then they speak from their own fixed utility function because like they have their own persona, like given to the LLM agents. And fourth, lastly, the planner makes some limited route edits to the first plan based on those critics. So yeah, throughout these processes, LLM is used for like language-related tasks. Persona agents read the plan, and then they explain the concerns from their perspective of personas given, and do the vote or do some comments. And then the planning agents also turns those concerns, like in the text, into some like route edit proposals. And then we are iterating up to T rounds there. And then second, the governance gates. A plan should be accepted only when all three gates are passed in the same round. So we check if there are sufficient consensus among the participants, if they meet some hard service threshold for unserved demand, because this is for the equity perspective of this public transit. And the lastly, fairness one, that limits that rejects the plan that concentrates cost on a certain group. This is for the fairness across the groups. And yeah, we did some numerical experiments using the two standard TNDP instances at different scales. One is Mendel, it has 15 nodes, and then the other is Mumford, it has 30 nodes in the network. And then the left one, Mendel, serves as a sort of like compact, small proof of concept. And then the second one tests like whether the conclusion survives in the larger and more heterogeneous feasible regions. And in every comparison, we fix the network and fix the OD demand. And then the differences are coming from different procedures, like whether they deliberate or not, whether they pass the governance gate or not. So yeah, and we construct some like one fixed population of personas, like it's a big population pool, P. And then we have different meeting profiles stratified by like income, different mobility, and neighborhood. And yeah, we have these 8 different meeting profiles as different sampling rules over that populations given. And yeah, so the arrow shows the arrow from the TVD 0 to TVD the bigger ones. The lower TVD means more representative to the actual population. So yeah, and the higher TVD, on the other hand, means more skewed and more biased. And these like 8 profiles are intentionally over-representing groups such as the car owners, retired homeowners, equity voices, transit-dependent residents, and whatnot. TVD is not a judgment over whether a group's concerns are legitimate, but it is a simply a controlled measure of like how far the meeting composition is from the representative meeting groups. So yeah, let me jump into the results. First of all, for the meeting composition sensitivity, at the aggregate level, we found that the effect was not as statistically significant on both benchmarks, but the tail results are more informative. The represented profiles tend to have lower worst case disparity, which is denoted as max delta CP, the disparity, and it also had the lower passenger cost. While the most skewed profile, if you remember the transit-dependent group, they tend to do worse in both measures. So, though I would not claim that composition is irrelevant, though composition does not strongly move the average, but still the representative sampling is directionally safer from the tail risk perspective. And the second part identifies the deliberation. And then we found that deliberation is the mechanism through which composition influence the outcome. In the no revision control, shown as L equals to 0 on the right, each meeting evaluates the seed plan, but does not generate any critics or route revisions, which means like in these runs, they select the same solution across all profiles. So the variation appears only when they do the critic-based revisions and deliberation during the meeting participants. And also we found that deliberation also like shifts the trade-off between the operator cost and the passenger cost. The operator cost drops sharply like when the deliberation is enabled. And also the direct service coverage, which represents some passenger cost, fails. Go down. So the deliberation is doing a job here, like where it chooses among different balances between the agency cost and the rider convenience. So yeah, the deliberation rebalances the plan towards the more operational efficiency, as you may see. And again, it is a channel through like which like those who participates can influence which part of the feasible trade-off space is selected. Okay, and for lastly, the governance gates, it mainly reduced the variation of the outcome rather than changing the average results. So among 3 criteria, the service gate, consensus grade, and fairness gate. The service gate is the most restrictive in the runs, with the pass rate of 44 to 64%, while the consensus and fairness gates pass more often. I think this is intuitive because like it is relatively easy to obtain the agreement on the proposal, but it's hard to satisfy the strict service constraint posed by the system. And the box plots on the right compare gated and ungated runs. On the left, the cross-profile spread in the passenger cost disparity is clearly smaller with the gates. And on the right, the mean passenger cost, the CP, distribution also improves with the reduced variances. The trade-off is smaller accepted. Um, the trade-off is a smaller accepted solution space. Some candidate plans are rejected due to these gates. So like that cost can be worthwhile when the objective is to improve the worst case equity. And as a side note, another lesson we learned from this is that the threshold value in gates must be calibrated for each network and planning context. So yeah, the limitation is like we use LLM agents as proxies, not validated with the real participants, and we also did the experiments on the toy network, and we also used a very small LLM backbone. Maybe we can do with the larger models with the reasonings or RAG or RFT, which is more fancier tools these days. And then yeah, our plan is to validate on some real world applications like MBTA bus network redesign examples. And also we want to calibrate against like observed participation records, like they have some transcripts of the public hearings. And then also we are going to try the different process protocols if those different protocols result in different outcomes. So yeah, the three key takeaways. First, meeting composition has limited effect on the aggregate performance, but like the representative sampling is directionally better than the other. And second, deliberation matters. Without critic and revision, all profiles return the same results. So deliberation was the mechanism that the meeting composition affects the plan outcome. And lastly, governance gates compress some like residual tail risk and make the outcome more consistent across the profiles. So yeah, we demonstrate that the structured deliberation with the governance gate process, we can observe some bias from the different meeting composition profiles during the transit network planning process. Yeah, I think this concludes my talk, and thank you so much for listening, and I'm happy to take any questions.
Thank you very much, Jung-Hoon. I have one question here for you. I think the talk was very inspiring and very promising in the results regarding a topic that is always critical and quite sensitive. So let's go with the question here. If there's time, there's Kiritaro Mori. She's saying, or he is saying, Kiritaro, he says, could you please elaborate a bit on the use of the LLM, especially how the agents interpret the transit network and how the deliberation is facilitated?
Yeah, sure. Yeah, LLM is used in two ways, I think. One is modeling the meeting participants. Like we give some persona to each agents. Let's say like you are 60 years old, retired homeowners, you have a car, you don't like public transit and whatnot in the text manner. And then yeah, LLM sees the transit network design with some like with some visuals and also with some audits of those programs. And then yeah, so that's like how we use LLM as a model of the human participants. And the deliberation is facilitated with like one moderator, and then we welcome like if any other agents have some thoughts or something like that, and then we just let them do some deliberation as they go on. Yeah, thank you for the questions.
Thank you very much. And we're going to go to the fourth talk of this session. And this is going to be in charge of, if I understand correctly, Javier Rueda. And Javier is presenting from the Instituto Superior Técnico from Lisbon with Víctor Cantillo and Filipe Moura. And the talk is titled, Do Interventions Encourage Sustainable Mobility in Schools? So I wonder, I think Javier is there. Can you please share your screen? Thank you very much, Javier. Perfect. Go ahead. No, can you?
Okay, can you see my screen?
No, we're seeing me.
Okay, now?
No. Can you make it? Yeah, but now please press in the presentation mode.
Okay, let me share it's a moment. Okay, okay. Now?
Yeah, but put it in the presentation mode, please.
Okay. Now?
Great. Go ahead.
Okay. Okay. Thanks for being here, for Herbie, and for her, and the others. Okay, my name is Javier Rueda, the author of this is our latest work that we are doing right now is regarding to intervention, how intervention encourage sustainable mobility in the schools. This is the structure of the presentation. The first is the introduction. Second, identify research gaps. Object is a methodological approach. General description of methodology, case studies, survey design, school interventions, and main findings. Okay, in the introduction, as we know, transportation plays a relevant role in economic mobility and urban sustainability. Researchers are agreed that home school trips are relevant in the throughout the students' life in their decision in the travel choices. And student that doesn't have activity in their life, they increase the risk of acquired diseases. This is relevant for Barranquilla. This is the context of the study to reduce private car and informal transport use because it can reduce the accidentality and another trouble that we have in road safety. The global south countries such as Colombia have difficulties in education, transportation, households. Okay, the objective of this work is analyze the influence of intervention, the student preferences and perception using hybrid discrete choice model. The participants in the first survey was 1566 students, and the second survey was 1435 students. Of this, 329 were control students. And after obtaining this data, we estimate changes in travel behavior, identifying the effects of this intervention on travel preferences and latent perceptions. Okay, the gaps that we identified, for example, few studies work in the global south regarding promoting changes in travel behavior. The majority of the studies focus on children rather than adolescents. Another gap that we identified, the majority of the studies uses a active mode, but they exclude most of the time public transportation. And in this study, we include public transportation. Another limitation is that the studies doesn't evaluate the interventions to promote shift towards sustainable transport modes. Few studies were found to do this, and in the literature was found few studies that were hybrid discrete choice model using to know how intervention influence in travel preferences and the perception of the students. Okay, we use a method approach, where qualitative method we work with students in the service to obtain the data, to gain the experiences, and to know the travel choices and their mobility. And we use a quantitative method to estimate statistical models such as the hybrid discretes model and another statistical analysis. Okay, this is the general description of the methodology. This project was applied in Barranquilla to 6 schools in Barranquilla. We conduct a first survey to collect data on travel behavior. After that, we implement the actions to promote changes in travel behavior. And after the conduct the actions, in a window of 6 months after the first survey, we conduct a second survey to know, to capture the data about the changes that the students have regarding their preference and their perception. And after that, we find the impact of this implement action on the students. The case study is Barranquilla. In Barranquilla metropolitan area has 5 municipalities, but this work was applied in Barranquilla because this is the biggest city in Barranquilla metropolitan area, and we applied to 6 public schools in Barranquilla because it was not feasible to apply to private schools. Continue. The survey design. We design a state choice survey to assess the impact of the intervention. The students belong to high school education in Colombia, and the participant feel or respond the question using their laptops, the laptops from the schools or their own smartphones. And the structure of the survey, we apply 4 types of questions. The first type of question were socioeconomic questions, for example, age, gender, vehicle owner, grade levels, income, etc. And the second type of question were perception questions. We found in the literature 4 pilots. For example, confidence, safety, condition for walking and cycle, and convenience. And the third type of question were regarding mobility topics. Some of these example of questions were current most frequently used for travel and walking time from home to school, among others. And the last type of question were state choice permit with 36 choice situations divided into 4 blocks with 9 hypothetical scenarios per block. Okay, continue. Sorry for that. Okay, these are the perception questions that we asked to students. Were 14 perception questions. The scale used is a 5 Likert scale question, where 1 was strongly disagree and 5 is strongly agree. Okay, the choice spearmint, we can see in this slide the spearmint in the left figure. We have the attributes. We use attributes such as travel time, travel cost, infrastructure, shower, hour, and we divide in short trips and long trips. We identify that a student that live more than 20 minutes in walking from home to school, they don't use walking, and this is supported by the literature. And the short trips, the long trip are the students that live more than 20 minutes walking from home to school. And in the right figure, we can see an example of the figure that we show to students in the experiment. Okay, we use 5 alternatives: private car, public transport, school bus, walking, and bicycle. Well, regarding the school intervention, we implement 4 types of action that were successful implemented before. One type, the first action that we implement was give to student information related to mobility. For example, importance of increasing physical activity, independent mobility, accidentality regarding private transport, or negative environmental impact of private transport. And the second action that we applied to a student was with a 50-minute lesson where a student shared the experience regarding their travel modes, or their travel to home, to school, or to school from home. And the third action was we implement a gamification activity. It's called My Path Towards Sustainable Mobility. In this gamification activity, they have, after the sustainability travel reflection, they have to fill in a sheet which they, in 15 days, they try to change to sustainable transport modes. And if they change, we give some awards to them because they have obtained the force to change. And the last action that we implement was a safety route. Is a really relevant action, because the objective was teach the student how to walk safely to school and give information on traffic norms, road signals, and pedestrian paths. Okay, now this is the structure of the hybrid discrete model applied to know the effect of the intervention. In the upper box, we can see the structure equation model. We can see the socioeconomic variables and the indicators, and the connecting with the latent variables. And the lower box, we see the choice model. In the utility function, we include 2 variables. One variable called intervention effects. This variable was included to know how intervention influence in each variable in the model. And the wave effects is to know how were the changes between the first survey and after, before the intervention and after the interventions. The main findings were that we found that intervention influenced the travel behavior to students, were, for example, influence positively preference for sustainable transport modes. A student that received the intervention perceive less attractive longer car trips. Moreover, they reduce the intervention, reduce the sensibility to infrastructure condition. It means that students that receive this intervention, they can walk and go by bicycle or by bus, and they have less importance the infrastructure conditions. And another is the increase student probability to accept longer travel time when choosing the school bus. And another finding is intervening student consider receive an hour less relevant regarding or to indifference with control students. Another finding is the intervention have positive effect on student attitudes toward walking. Finally, positive influence on perception such as confidence in their abilities, especially among middle-income students and those from car-owning household. Thank you.
Thank you very much, Javier. So if there are questions for Javier regarding this approach for addressing a student environment so that make it better and safer, I will be pleased to read them from the chat. No? So let's move then to the next talk. This is going to be again from a Spanish-speaking, I guess, Colombian person from Sebastian Reyes. Is Sebastian around? Sebastian Reyes, impacts of the TransMiCable on urban development in Ciudad Bolívar. Is Sebastian? Yeah, so he's there. Can you please share your screen, please? And Sebastian is asking for his mic to be open, please. Lika, I don't know if you're in charge. Yeah, now Sebastian, please. If
Now,
you
now you hear me?
Yes, we can hear you. Could you please make your screen wider?
Yeah,
Presentation
yes,
mode.
for sure. For
Please
sure.
go ahead.
Yes. All see the screen?
Yes.
Okay, thank you for the space. This is a investigation that we do between Luis Ángel Guzmán and Santiago Gómez Cardona. The title is When Accessibility Reshapes the Periphery, Aerial Cable Cars and Informal Urbanization. So, what we know? We know that the transport infrastructure give us a better accessibility to our territory. So, this provoke a territorial integration and new development pressures. So, can improving accessibility also reshape the urban frontier? Is the question. For this case study, I want to bring all of you to the city of Bogota, specifically the southern of Bogota, in the Ciudad Bolívar. Ciudad Bolívar is a historical neighborhood that becomes or born like informal neighborhoods. The majority, the 96% of the households is in the lowest socioeconomic tier. And in 2018, the system of TransMiCable opened with 4 stations and 3.4 kilometers that connecting thousand of people to the network of the BRT system of Bogota. Now, how did the urban frontier change after the TransMiCable? We know that the accessibility of the TransMiCable generated by the TransMiCable gives a reduction of the travel time to 16 minutes to 13 minutes. So it's a big change in terms of travel time. Also, we know that the people start doing more healthy activities and increase the satisfaction with public transport. Now we can see how the urban footprint between 2012 and 2024 changed. In the start, we have 20 hectares of urban footprint, but after the TransMiCable begins operations, the urban footprint changed and increased 10 times. So we have now 200 hectares of urban footprint. These urban footprints, it is not a formal development. Why we know that? We know that because the government doesn't have the information and the record of this development in this land. So we propose a methodology of logic model. This logic model allow us calculate the probability of one part of land become urbanization. In this case, informal urbanization. For this, we have a training variable that calls cable. It's a variable that it starts in 1 when the cable car begins. We have also a network distance to the nearest high capacity public transport station. That is the station of TransMiCable when the TransMiCable starts, but before the TransMiCable is the BRT network of the system of Bogota. Also, we have terrain slope distant to the formal urban edge, like parks, also the urban amenities, like parks, schools, and police stations. And we have a few of interactions between cable and the variables capturing physical and proximity constraints, like slope and the proximity. Now, how we construct the data? We know that this kind of development is irregular growth, so we have to standardize the units of the analysis. We determine grids of 50 times 50 meters that assimilate like a normal development neighborhood in Bogota. The result of that is that we have 2,000, near of 2,000 cells. So in this map, we can see that the cells have different colors. These colors are from the year that the cells start beginning the informal development and the clustering of the spatial development. So we have a panel analysis of 5 periods, and we have different transitions cells that urbanizates between each year. Now, going to the results, we have the principal model that we choose. We choose this model. We start doing a basic models to going to this model that allows determine the heterogeneity between each cells. So we have the results of cable, slope, proximity, distant to the formal edge that have the service, and the interaction between cable, slope, and cable and proximity. Now, how we can interpret these results more easily? We calculate a marginal effect of each coefficient. How? We first calculate the average of the urban informal transition, and is 15%. So we start with this 15% and start calculating each marginal effect. What is the principal results here? Here we can see that the proximity before the TransMiCable start, each additional kilometer from the high capacity public transport reduces the probability of informal urbanization. Also, the slope, each additional degree of slope reduces the probability of informal urbanization, approximately in 1%, and in proximity 14% for each kilometer. Now, when the cable car starts, we have the variable that interact between proximity and slope. Here we can see that now with the TransMiCable substantially attenuate the negative effect of the distance to high capacity public transport. Also, we have that the slope change the sign, and the TransMiCable change the effect of the a big slope in a development in different hills in this part of the city. So the cable car sustainable reduce the constraints imposed by proximity and terrain slope of the informal urbanization. Here we have a few of findings. Key findings, we have the TransMiCable is associated with a spatial reconfiguration of the informal urbanization. Also, we have that the system attenuates the constraints imposed by accessibility and terrain slope. And we have that the transport instruments can redistribute not only accessibility, but also the territorial initiatives underlying informal urbanization. So this is an important study for Bogota, because Bogota is planning to expand the network of the cable cars in the peripheral areas, like the others Latin American cities. So a project that improves the accessibility also can generate in a difference changes in the urban development. Here we have a few limitations also that not external control group, because this is the first cable car in the city that works in this way. Also, we have the period, we don't have fixed effects because the variables doesn't change between the years, so we don't have this kind of control. And the spatial depends. We do we calculate the standard errors with clustering the differences by year and located, but also is a limitation. So thank you very much for your attention.
Thank you very much, Sebastian. Very interesting results. I wonder if I mean the research you show predicts or explains that the presence of the TransMiCable was able to trigger some urbanization close to the cable, correct?
Yeah.
Did you find any impact on the density of those urban developments? Like if the kind of housing that is developing near the cable is more dense than maybe far away from it?
In the nearest houses of each station, we don't have the information of the density, but we have the information that the peripheral area of the least station grow a lot of. Yeah, we can see in these images this kind of house neighborhoods. Before the cable car start, this was only a Greenland. Yes, so we know that the density grow. Also, we know that the price of the value of the square meter increase a lot of. We are doing right now another investigation about that, and we know that the value change a lot.
Thank you, Sebastian. So good luck with your research. I hope you can publish it soon. So let's move now to the last talk of this session. I can see Olga already connected. The talk is gonna be is coming from Olga Bredikina, who's right there, with Elizabeth Petit, which I also see connected, and Renu Dalal, which I'm not sure if his or her is connected, but the talk is called Workforce Readiness for Battery Recycling and Second Life Applications. Our talk is a little bit different from what we've heard today, but we're eager to learn from your research. Olga or Elizabeth, I don't know who's. I guess Olga will be presenting.
You're
If you
okay.
could,
I've got our slides here.
you could share your screen, it would be great.
All right. And can you all see that all right?
Excellent. We're not really seeing the very large screen. We're seeing a sort of presentation where we see all your slides on the bottom. That's better. No, that's great. Please.
Perfect. Now,
Thank
is
you.
this, it's not going to let me do what I would like to do. Give me just one moment here.
Sure.
All right, that's okay. It just is not letting me have my notes up. No worries. My name is Elizabeth Pettit. I work here at the AMP Center, which is the Alabama Mobility and Power Research Center at the University of Alabama. I am our workforce development lead, and I am here with Olga, who is our research transportation manager, and she handles all of our business intelligence as well. We are here to present, as you said, kind of a little bit of a different paper. We researched workforce readiness in the battery industry pertaining to second life applications and recycling of batteries. So we did not have a formal research study with papers, but rather a literature review. So by 2032, it's projected that the EV and battery manufacturing industries combined in the US alone will require between 160,000 and 195,000 new jobs just to meet the projected EV demand, which of course can shift around. The workforce development piece of the EV industry in the United States does face several different interconnected challenges, which include a shortage of specialized training programs, significant skill gaps, as well as the need for stronger coordination among industry, educational institutions, and policymakers, which is an issue that here at the AMP Center we are trying to solve. The central research question to our paper was what gaps exist in workforce development efforts of the EV battery industry, specifically the second life applications and recycling and resource recovery stages. So as I said, we did do a scoping review method designed to identify those key themes and gaps. And our sources were pulled from EBSCO database, government websites, publicly available industry platforms, and we included a total of 51 sources for the full review. So the battery life in the electric vehicle economy starts with raw materials mining. While sustainable sourcing of raw materials required for today's battery production levels remains feasible and easily completed, the projected exponential increase in EV battery demand by 2050 is, of course, expected to impact this somewhat negatively. By 2040, the demand for lithium and cobalt could increase up to 8 times current levels, which we cannot currently support. Fully developing the raw materials mining industry within the US is essential as it enables batteries to be used for second life purposes and then further reduces the need for newly extracted raw materials, even amid that rising demand for batteries. Following raw materials mining, we move into the use of batteries in electric vehicles. So job roles within this phase relate to EV manufacturing, charger installation and maintenance, and general electric vehicle maintenance. Sufficient knowledge has been generated about the beginning of life stage of EV batteries, while both the midlife and end of life stages had very little research that was currently available. And past that, we move on to the second life application stage. So after an EV battery completes their operational use or their first use in an electric vehicle, they transition into either the second life application stage or recycling and resource recovery. Here we will cover the second life piece. Batteries are, of course, routinely repurposed for different things such as energy storage in both commercial and residential settings to help manage peak power usage and reduce the impact of power outages. And this is done in several other countries, just not currently in the US. By implementing second life battery applications, the need for raw material extraction can be reduced and contribute to a more sustainable EV battery ecosystem. So again, lessening the need for that newly mined materials on the raw materials manufacturing side of things. And then repurposed EV batteries are one of the key economic alternatives to new utility scale batteries, which directly appeal to US policy goals as well as CE principles, which Olga will speak to shortly. If we were to go the route of recycling resource recovery, the available research and data on battery recycling was also kind of very limited, actually. Only about 10% of the current lithium-ion batteries are being recycled, and the battery recycling industry remains in its very early stages, as well as holds significant potential for expansion here in the United States. Currently, China handles over half of the world's battery recycling, and Europe accounts for approximately 36%, while the US holds just 6% of that. So this is an area where our workforce can really grow and build up the economy in the United States. An estimated 156.7 gigawatt hours of EV batteries are expected to require routine recycling by 2030. So that is coming up very quickly and will require a very strong workforce to do so. As we transition away from kind of the battery life cycle into the circular economy of batteries, just some more background information on that. That circular economy promotes the concept that any remaining energy or materials in the electric vehicle battery, once they have been fully used in the electric vehicle for its primary function, should be recovered and utilized to its fullest potential before being discarded. This plays directly into the second life applications as well as recycling and recovery stages. So challenges here include inconsistent battery designs, varied recycling methods, the hazardous nature of recovering residual energy in materials, as well as a lack of robust infrastructure to support large-scale recovery and reuse, endeavors in the United States. The European Union has circular economy frameworks built into its rules and laws, but the US's approach is mostly market-driven and fragmented, so we are significantly behind other countries in that area as well. Reusing EV batteries after their operational life does offer highly valuable pathway for supporting a circular battery economy. And then EV battery recycling and resource recovery industry could grow by more than 20 billion by 2030. So again, just a very quickly approaching deadline that is very valuable for us. On this first section of the paper, some research and knowledge gaps, there was very little information. Of course, areas are very critical to industry advancement and sustainability, as well as innovation in battery design, which will push the circular economy forward. And then further exploration of repurposing strategies and second life applications for used EV batteries is needed to support that circular economy, those goals in the United States, and extend battery value beyond its initial use. And with that, I will turn it over to Olga to present on the second portion of our paper.
Thank you, Elizabeth. Next slide, please. As Elizabeth mentioned, the growing demand for workforce in the battery industry and battery recycling sector can be explained primarily by the fast growth of the industry in the past decade and the continued growth. So in the right bottom corner, you can see the chart displaying the deployment by applications for lithium-ion batteries, and we can see that the demand has grown by a factor of multiple times over the last decade, and in the next few years, it will continue growing by up to 7 times by 2030 and up to 12 times by 2035. Therefore, significant investments in infrastructure and refining are necessary. We're also likely to see a growing diversification of markets. While previously battery industry, battery production and recycling have primarily been concentrated in China, we will see more developments in the domestic market in the US, as well as investments in the domestic market in Europe, and the investments by the European Union in battery supply chain projects in other countries outside of China, including Canada, Greenland, Kazakhstan, Norway, Ukraine, Zambia, and others. Next slide, please. Along with the growth in the battery industry, there has been a rapid growth in global recycling capacity, and recycling capacity is necessary because it helps reducing the demand for critical materials such as lithium, nickel, cobalt, and others. In 2023, China accounted for around 80% of global pretreatment and material recovery capacity. By 2030, it's expected to retain about 80% of global pretreatment capacity and 75% of material recovery capacity. Importantly, the recycling capacity is expected to outpace the feedstock for the next few years. But once the large wave of electric vehicles that are currently in operation begins to retire, we will see the decrease in the recycling capacity relative to feedstock. In the US, we may see the excess capacity eliminated after 2030. And then in India, it will decrease to be only about 10% by 2040, while China is still likely to continue experiencing excess capacity. Next slide, please. As Elizabeth mentioned, currently there is a shift towards a circular model as opposed to the model that was adopted in late 2010s, extract, use, dispose. Currently, we're moving to the model where batteries are collected, dismantled, processed into battery-grade materials, and integrated into production. The transition has accelerated in North America and other regions. In the US, it's driven by both major initiatives from US DOE, funding and partnerships for large projects, as well as automakers introducing in-house recycling capacity. Next slide, please. Integrated battery recycling business models include vertically integrated recyclers, which manage the full value chain from end-of-life battery reverse logistics to the recovery of battery-grade materials, cross-value chain partnerships that bring together companies from different sectors across the recycling value chain, and in-house recyclers that focus on on-site recycling. And example is the Brown Recycling in China, which is majority owned by CATL, the world's largest battery cell manufacturer. Next slide, please. Regulatory and policy landscape. We can see regulations that are that allow managing the battery recycling industry both at the international level as well as national level. At the international level, it's the Basel Convention regulations, EU battery regulation, as well as country-specific extended producer responsibility policies. In the US, we can see the regulations both at the federal level, such as the Resource Conservation and Recovery Act and Universal Waste Rule, US DOT Hazardous Materials Regulation, EPA regulations, as well as state-level extended producer responsibility laws. Next slide, please. And as far as industry and policy research gaps, we identified the need for more empirical research evaluating the performance of recycling technologies and business models across different markets and jurisdictions, policy and regulatory impacts, particularly assessing how existing and emerging policies, including recycling mandates, EPR or extended producer responsibility requirements, how they affect recycling investment, capacity expansion, and market development across different jurisdictions, and likewise how battery manufacturing capacity, energy and labor costs, transportation networks, and regulatory environments can affect the economic viability of this industry, as well as the location of recycling facilities. Next slide.
All right, thank you so much, Olga, for that policy piece. To wrap us up, I will share a little bit more on these specific workforce demands. So just a general overview, only a handful of the qualitative and quantitative studies that we reviewed have analyzed workforce demand and occupational trends within the EV battery workforce for the near future. This was also a very scarce information area. So many sources project a significant increase in demand for the US EV battery workforce in the coming years, which will be tied to the increased demand for electric vehicles that is projected. The existing workforce projections have not clearly identified the specific skills that will be required of that EV workforce, aside from giving us a number. Those projections indicate that most new EV battery jobs in the US will come from the battery manufacturing and production of batteries, as well as those various electric components that will go into the vehicles. The vehicle assembly roles are expected to remain comparable to those that are currently in the ICE engine workforce. The EV battery workforce in the US faces a talent shortfall with a supply to demand ratio of 1 to 1.8 for skilled technical workers with transferable skills in the EV battery manufacturing, and 1 to 1.4 for roles directly linked to EV battery production. So both of those indicate a significant shortage of qualified workers, even though they still have transferable skills. Programs offering industry-recognized credentials and certificates developed through partnerships hold the greatest potential for success, and that is another thing that we are hoping to kind of bridge the gap here at the AMP Center. So gaps in workforce readiness. This paper certainly gathered a lot of information that emphasizes the importance of skills such as problem solving, active learning, and the acquisition of technical knowledge and skills. The need for collaboration with industry professionals to develop those skills alongside effective EV battery workforce training programs is very high. None of the reviewed sources explain how this alignment is achieved or assess whether any existing programs effectively incorporate industry feedback into their design. 82% of current EV battery workers lack those necessary skills to fully participate in the industry, and the largest deficits are found in the upstream and downstream roles, mainly in that chemistry-related area. So most employers report that up to 50% of their current workforce requires reskilling or upskilling to remain competitive within the EV industry. And in reviewing best practices and emerging training models, there were a few from other countries that we can kind of pull some information from. EV battery workforce training programs are most successful when they bring together industry, academia to provide streamlined, industry-aligned, and industry-backed curricula. I know that is a lot of information there. Key factors distinguishing successful programs include on-the-job training, professional development, and continuing education components that facilitate the upskilling and reskilling of the current workforce because the industry is changing so rapidly. And then detailed knowledge of specific skills required across the EV and battery industries does remain very limited, again, just because everything is changing so quickly. And just a little bit more on this visual here. So at the AMP Center, it is our main goal to bring together government, industry, and academia. So we do try to facilitate all of that through different curriculum creation at both the K-12, two-year college, and four-year college level. And then workforce trends, different gaps that we had seen in this research here. A pressing need does exist for deeper understanding of labor force inequities, particularly in terms of access to training, job quality, and representation across different demographic groups and geographic regions. As the research was already very limited, these nitty-gritty pieces were even more so limited. Research is needed to evaluate the adequacy of current safety protocols and to develop targeted training programs that equip the EV battery workers with the necessary skills. A big one that we did find was that high voltage safety training. Evaluating existing workforce development initiatives for their effectiveness, scalability, and alignment with industry needs does remain a key priority, particularly again as the industry just evolves so quickly. And then despite the growing importance of circular economy practices, very few studies have examined that workforce readiness in midlife and end-of-life battery stages. So here, the early life, those first stages were well researched. And then in conclusion, our findings emphasize once again that strong collaboration between industry and education is essential to the future of both the EV and battery sectors within the US, and that these two sectors must work closely with policymakers to develop aligned strategies and programs. There is an urgent need for research that addresses labor force inequities, safety training, and operational challenges across the EV battery lifecycle to support equitable, efficient, and sustainable workforce development. And then our main piece here was a threefold need for future progress. So first, the US must develop a robust, industry-backed EV battery workforce training program that prepares workers for all stages of the battery life cycle. Even though we would like to focus on reuse and recycling, we do need to ensure that all stages are supported equally. And then second, the US needs time to build this critical infrastructure. Nothing will happen overnight. And lastly, the battery and EV industries require additional research across all life cycle stages, particularly related to workforce needs. As workforce is not really an area where you can do a hard number study at first, research is very limited before then. And that is the end of our presentation.
Thank you very much, Elizabeth, Olga. This is a very important topic. In my country, I'm from Chile, and we are also in the implementation of a law which is not being enforced yet in the case of the batteries on how to make the responsibility of recycling part of the companies that are introducing those materials into the market. And I can see that this is happening elsewhere too. So very, very attractive. I wonder if there are questions from anyone in the audience. Well, otherwise, I will conclude this session. Thank you very much to the seven speakers, because in this one we had two. So thank you very much, and I hope we can meet soon, eventually face to face, and not only through the screen. Thank you very much. Goodbye.
Thank you.